Hello students, next we look into the AC Thevenins Theorem, AC for alternating current. So we know that AC currents or AC networks generally consist of elements like inductor, capacitor, and AC voltage and current sources. Up till now we have studied Thevenin theorem and Norton's theorem for DC circuit. Now we are coming into the AC network. Is there any special change? See, there is no change in the statement because basically the Thevenin's theorem was done for DC circuits and it is extended towards AC networks. That's all. So there is no special theorem, Thevenin's theorem for AC. The only difference is that instead of writing RTH, the Thevenin's resistance, we are having here ZTH, which is the Thevenin's impedance. Thevenin's impedance. So that's the only difference. Instead of RTH, we will be having ZTH. Rest, the methods, the steps are all the same. So let us look at one of the problem. So the question asks, obtain the Thevenin's equivalent network for the terminals A, B in the figure shown. So basically what it is asking us to do is find out VTH and ZTH. We know the step. Let us do one by one. So step 1 is find VTH. Step 1 is find VTH. So I have redrawn the circuit and let me write the voltage VTH here because that's what I want to find, and then I will write the current. Now one of the things that we can do is, which I would recommend all of you to do, is that you redraw this circuit in such a way that it is very simple to see. For example, this 3 ohm resistor and capacitor I can write together because they are in series. Okay, they are in series, so I can write them together as a single element, and a single element is represented by this rectangular block, and 3 plus minus J4 will give me 3 minus J4. So I will write this as 3 minus J4. Okay, so this becomes 3 minus J4 ohms. Why? Because it is in series. Now similarly 4 ohms and J6 ohms, the inductor, is also in series. Why? Because their two terminals are touching each other and there is a now third terminal from there. So both of them are in series. So I will write them also as a single value, as a single equation. So let me draw that. So that also I will draw it in the shape of a rectangular box, and I will write its value as, see, it's a combination of 4 ohms and J6, so I will write it as 4, let me use a different color, I will write it as 4 plus J6 ohms. Okay, similarly I will write J5 and minus J4 together as a single element. That also I will write it as a single element. So let me draw a box here and I will write them together as J5 minus J4 becomes J. So 5 minus 4 is 1, so it just becomes J ohms. So I should use a different color. Okay, so it becomes J ohms. So now the circuit looks much neater. It looks much neat because now both of these together can be written as a value. No need to write them as separate value and the equation becomes very big. So now this is much manageable. So now let us write the KVL. Okay, so I will write KVL at mesh 1. So we know that if the current is traveling like this, entering, leaving, entering, leaving. Here there is no current. Why? Because this is open. So there is no current here. Okay, so I should not write any current here. So therefore, if I take from back of the bogie, then it becomes minus 50 angle 0. I can just write it as minus 50 plus 3 minus J4 into I plus 4 plus J6 into I is equal to 0, from which I can write 3 minus J4 and 4 plus J6 both have same I as the multiplying factor, so I can take I as common. So I will get 3 plus 4, I will get 7, minus J plus 6J will give me plus 2J I, and I will take the 50 the other side, so it becomes plus 50. Okay. So with that, I can very clearly say, therefore, I is going to be equal to 50 divided by 7 plus 2J. We'll find the answer. So this is basically the KVL at mesh 1. Next, we can find out, with the help of that, we can write the KVL at mesh 2. Okay, so before that, let me find out what is the value of I, because I will use that. Okay, so using a calculator, I can find out its value 6.87 with an angle of minus 15.94. You can check with the calculator. Okay, now when we look at mesh 2, so at mesh 2 there is no current, but there are voltages. So this is one voltage, here there is going to be no voltage, but so I will just write 0 volt here because there is no voltage there. And then there is plus VTH. So let me write it as from back of the bogie. So I will write minus 4 plus J6. Okay, so from back of the element I will write minus 4 plus J6 plus VTH. So 4 plus J6 into I, into I plus VTH is going to give me 0. So you might be wondering, why did I write plus minus here? Just because I current is flowing from top to bottom. So this is going to be plus, this is going to be minus. Okay, now if I am going to write some current here, then I will consider this as plus and this as minus. That's true. But here, it's, since that current is going to be 0, 0 minus I, it's again going to be minus I. So it again the polarity will change. So it's writing one and the same thing. Therefore, I can write VTH to be equal to 4 plus J6 into whatever we have found out just now, 6.87 angle minus 15.94, which when I solve, I get the answer as 49.5 angle 40.36 volts. Okay, that is going to be the VTH. And then we have to find out, in the next step, we have to find out step 2. It's going to be find ZTH. Okay, so again we have to draw the same diagram. So let me draw that. So as you can see, I have redrawn this, and now we have to find out ZTH, for which we will have to short the dependent sources, voltage sources, and open circuit the independent current sources. Let me again say it because I think I said something wrong. The independent voltage sources have to be short circuited. The independent current sources have to be open circuited. So here we are having only voltage source. So I will just short circuit this, don't require it. So let me use a different color. So I am short circuiting this. Now as you can see, let us find out what is the ZTH value when we look from here. Now I have already told how to find if some element is parallel with something else. So as you can see here the element 3 minus J4 is, it looks like it is in series with J ohms, but there is a third element coming from here. So 3 minus J4 and J ohm cannot be in series. But the other end, if I take of this one and I bring it here, these are the two ends of this element 3 minus J4, and this element will have its two elements touching the first two. So these two are going to be in parallel, and that if I would draw it, okay, before drawing let me draw it and then write the value straight away. So what I will be having is, I will be having a single resistor, not resistor, a single element which is the parallel of both of this, and then the remaining J ohms is as such going to be there, okay. And then I will have to look from this side. So here it's going to be 3 minus J4 parallel with 4 plus J6. Now I had seen some of the assignments, some of the tutorials being done by students where they calculated this extensively. See, in the calculator all you have to do is 3 minus J4 the whole inverse plus 4 plus J6 the whole inverse bracketed with the whole inverse. You have to write this as a single equation in the calculator, because that will only give you the shortest step to find out the parallel value. Otherwise, if you are going to do it on paper, it's going to be really lengthy. Okay, so remember here to keep the brackets as such. If you are not keeping the bracket, you will always make mistakes. Okay, so if I do this in calculator, if I calculate this, I will get the answer as 4.95 with an angle of minus 12.765, or I can omit the 5, no problem. Okay, and that is in series with J ohms. How is it in series with J ohms? Again, for explaining, J ohm has two terminals, one is this one and the second is this one, whereas this particular element has one terminal here and the second terminal here. Okay, so when two elements are having a common node and there is no third node coming out from that, then both these elements are going to be in series. So all you have to do is we have to add with J ohms, and then we will get the answer as 4.83. so that, let me write it. So I will get, therefore ZTH is going to be 4.95 angle of minus 12.765 degrees plus J ohms. And that gives me the answer as 4.83 with an angle of minus 1.12. Okay, so now we are having both VTH and ZTH. So now I can very easily draw this, the Thevenin's equivalent as, so plus minus, this is the AC voltage, and this will be the impedance. The impedance we have already found out, it is 4.83 with an angle of minus 1.12 degrees, and the voltage VTH we have already found out is 49.5 with an angle of 40.36 degrees. That's what we found out here, correct? So this completes the problem. Now they have not given any load resistance or load impedance. If there would have been some load impedance here, then we would have had to keep that same load impedance here and then try to find out what is the current flowing through and all. But that is not there in this problem, so there is no need for us to do it. So as you can see, the steps are all the same. The only thing is that here we are having elements which are complex in nature. That means you are having the imaginary components also coming because of the inductance and the capacitance. And always remember to make this shortcut of making the elements, combining the series elements to make it as a single one, so that your equation looks small and neat. Otherwise this would have been looking very, very long, and that's going to be really headache for you. But when you do this, you have to be very careful. Many students make a mistake while doing it because they don't realize which all are the series elements. So if you are not clear with if two elements you are able to find they are in series or they are in parallel, then please go back to my videos and study those, and then only you will be able to understand this. Okay, thank you.